mean value theorem, this is another theorem to have on your little card so you can memorize what it's all about so that you can state it if you were to justify an answer. So the mean value theorem is used to determine which critical numbers for a function correspond to local extreme values. So remember last lesson we were talking about the extreme values. Now we're kind of making that a little further. So mean value theorem for derivatives is a huge theorem. We abbreviate it NVT. If a function f of x is closed, remember it has n points, and differentiable on an open interval AB, then at least one C between AB, that's not a point, that's an actual interval from A to B, exists such that the derivative at f of c is equal to the slope of the secant line, essentially. That's what f of b minus f of a over b minus a represents. So here's a visual of what they're trying to say. They're trying to say between a and b on this curve, there happens to be some point c that the derivative is the same as the derivative going through these 2 points. And that would show that they're parallel if they're the same slope, right? So, okay, so geometrically this means the slope of the tangent line will be equal to the slope of the secant line going through A and B for at least 1 point on the curve, at least 1 point. So NVT can also be rewritten if I cross multiply this B minus A up. Do you see that I have f of B minus f of A is equal to the slope at C times B minus A. So here's a graph, and it's saying mark on the x-axis points C in the conclusion of the mean value theorem. So the first thing I would do is actually make a line going from A to B. So here's A, so like that. That's not a very good line. Maybe I should actually use the line feature. I'll just do that. Yeah, so even with the, I'm just going to see if I can, I'm going to make it a different color just so it, I thought I could make it a different color. There. Okay, so there is my line going through AB. So can you find a point C? Can you, that would have the same slope when you make that tangent line? What do you mean by in the middle? Like right here? But the, just so you know, the tangent line here would be going like this. It has to be the same slope. I'm sorry? Yeah. So I'm going to use a blue pen here. I heard this. So here's a tangent line, say, going like that. So there's, say, C1. Or actually, I should be doing it like this. Here's C1. Is there another one? Yeah, at the bottom. Oh. So right there. C2. Okay, so everybody know what they're looking for? So we're looking for the tangent lines that would be the same slope as the secant lines. All right. So in the next one, we're going to show that the function f of x equals x squared satisfies the hypothesis of the MVT on the interval 0. That should be 0, 2. I don't know why it looks like 0.2. 0, 2. Then find a solution C to the equation f prime of c equals f of b minus f of a over b minus a on this interval. So I gave you a visual of what this looks like. I would hope that you guys know that x squared is a parabola. You're like, grade 11 was all about x squares, right? So here's x squared. We're going from 0 to 2. And then I basically connect 0, 0 to 2, 4 here. And made that secant line, right? If you want, I can use, just so you can see it better, I'll make it in green, going like that. There's the secant line, right? Okay, so now does everybody see the same slope would be right here? Yes? Okay, so, and we don't necessarily know that it's at 1, 1. That's the answer. So we got to figure out where it is. Okay? So first off, we need to find the slope of that secant line. So what is that slope? Yeah. How did I get 2? It's like grade 10 math, right? I'm going to measure. I went up 4 over 2. That's a slope of 2. So slope of secant is 2. You could also do it as m equals, if the 2 points are 2, 4 and 0, 0, you could have also done it as using this part of the equation right here. And that would be 4 minus 2 over 2 minus 0. And I would get 2 over 2. Sorry, I'll try that again. 4 minus 0 over 2 minus 0 gives me 4 over 2, which is 2. Either or, we get the slope of the secant line to be 2. So now we need to find where this tangent line is that same slope. So how do we figure that out? Nobody wants to find the derivative of this? Yes, f prime of x would be 2x. So I know the answer is right here, 1, 1. But I don't know where it is at this point, right? So, but I do know that this has to equal that, right? So I set 2x equal to 2, and I solve that x is 1. And then all I have to do then is find f of 1, which is 1 squared, and I get 1. So therefore, actually it's only asking for c. Therefore, c equals 1. What do you think about that? Okay. Let's try the next one. Verify the conclusion of the mean value theorem for f of x equals x squared minus 3x minus 2 on the interval -2, 3. All right. So what do we have to do first? Find the secant line. So we need to find the slope of the secant line through endpoints x equals -2 and x equals 3. But before I can do that, I need to know what the y values are, right? Because in order to find the slope, I need y2 minus y1 over x2 minus x1, right? So when x is -2, we plug it into this function. We get 4 plus 6 minus 2, we get 8. Yes? We plug 3 in. 3 squared is 9 minus 9 minus 2. So I get minus 2. So now we're going to find m. Remember m, y2 minus y1 over x2 minus x. So 8 subtract -2 over -2 subtract 3. So I get 10 over -5, which gives me -2. So now I need to find the derivative. Okay, f prime of x is easy now, right? 2x minus 3. So the derivative has to equal the slope of the secant line. So I set them equal to each other. So -2 equals 2x minus 3. Move the 3 over. I get 1 equals 2x, so x equals 1/2. So technically, I don't actually, the conclusion of the mean value theorem says that there's a C, like if I were to read the theorem here, it says, if f of x is continuous on closed interval a, b, and differentiable on an open interval, then there's at least one point C. So here's the x value of that one point. To be safe, you could calculate the y value, because it's not actually saying that, but really C is that. So therefore, there exists C equals 1/2 in MVT. Something like that. All right. So far, so good. That's pretty easy stuff. It's kind of like the extreme value theorem was. Increasing and decreasing in constant functions. Recall that a function f is increasing on an interval I means the graph of f blank as you move left to right. What is it if it's increasing? Rises. Rises as you move from left to right. It has to be rising. Hence, the slopes of the tangent lines are, it's rising, positive. So here's your first theorem that basically tells you that. If f is differentiable on open interval AB, and if f prime of x is greater than 0 or positive, meaning the slopes are positive for all x between that interval, then, I don't know why it's not on the next line there, but then f increases on AB. So it's basically saying what you visually see if you think about a line. If it's rising from left to right, all the slopes on there are positive. If you have a curve going like this, or I guess it shouldn't be going like this, but if all the slopes are positive, then it has to be increasing. So recall that a function f is decreasing on an interval I means the graph of f falls. I don't know what, you could use it another thing. As you move left to right. Hence, the slopes of the tangent lines are negative. Okay, so here's the theorem that says if f is differentiable on interval AB and f prime of x is less than 0, for all x's between a and b, then it decreases. So, recall that a function f is constant on an interval means that the graph of f is you could say it's constant, but I guess visually it is horizontal. I don't know. As long as you know what it means. As you move left to right. Hence, the slopes of the tangent lines are 0. Yeah, 0. Very good. So here's the theorem that says this. If f is differentiable on AB and f prime of x equals 0 for all x's between a and b, then f is constant. So here's the summary. A function is blank over an interval if the derivative is always positive. A function is increasing. Very good. A function is blank over the interval if the derivative is always negative. Decreasing. A function is neither blank nor blank, then the derivative is 0. Yeah. Find where the function f of x equals f of x equals 3x to the power 4 minus 4x to the 3 minus 12x squared plus 5 is increasing, and where it's decreasing. Here's the visual. You're not supposed to really use the visual because you wouldn't have that on the exam. You actually have to figure it out. So, what do we have to do here? Find the slopes. Okay. Between each turn. I like it. I like it. Okay. So how would we do that? You find a max or a min. Very good. That's the turning points, right?
You do something we did yesterday.
And we do something we did yesterday. Right on. Okay. So how do we do that then? We find the derivative. You should always start, like honestly, the whole, first semester, that's all we're doing is derivative, right? So f prime of x is equal to 12x to the power 3 minus 12x to the power 2 minus 24x. You know, we graphed f of x equals 3x to the power 4 minus blah, blah, blah in grade 12 math, right? And the way we did this was we found all the x-intercepts, and then we know it opens up. And we didn't care where those local max and mins were, right? Remember I said to you, well, in calculus, we're actually going to figure out where they are, and thus now we are at that point. We have come so far. Okay, so anyways, now what do? Yeah, no, you have to factor, but at the same time as factoring, what am I going to do? How do I find the maxes? Yeah, because at the max, the slope is 0, or the min, the slope is 0. That's what we learned with the extreme value, right? Because we're not going to get an undefined thing. It's only when it's 0 we're looking for in this, right? So 0 equals, and then I heard I had to factor. So what's a factor?
12x.
A 12x. Very good. And then I'm left with a quadratic, which is nice, minus x minus 2. So that factors to be x minus 2, x plus 1, which means there's critical values at x equals 0, 2, and negative 1. So I need to figure out where it is. Remember when the derivatives or the slopes were positive, that means it's increasing. When the derivatives or the slopes are negative, that's where it's decreasing. So guess what I'm going to do? I do the old-fashioned sign diagram. So this sign diagram doesn't represent the x-intercepts. It actually is representing the turning, or the maxes and the mins, right? So I'm going to put negative 1 on here, 0 on here, and 2 on here. Do you remember how we did this? Remember I'm trying to find where the slopes are positive or negative, right? So that's why I'm labeling f prime. If you don't label it, they might think it's f, so you gotta watch that. So I'm gonna pick a number that's on the left of negative 1 and plug it into here, right? And I don't care about the number, I just care about the sign. So negative 2, if I put it in here, I'll get negative. If I put it in here, I'll get negative. And if I put it in here, I'll get negative. So I have 3 negatives, which means it's negative. Let's put in, say, negative 0.5. You don't have to have it exactly halfway between the two. But anyways, negative 0.5. So this would be negative. This will be negative. This will be positive. Yes? So what do I get overall? Positive, because I had 2 negatives. It's not always going to go negative, positive, just so you know. Okay? In this case, it does, but it's not always going to be. So don't think that there's a pattern to it. Okay, so now I'm going to put, say, 1 in there. 1 I get positive. 1 in there I get negative. 1 in there I get positive. So I get negative. I'm going to put, say, 3 in here. 3 goes in there. Positive, positive, positive. Okay. So what does that mean? Yeah, so therefore it's decreasing in which intervals? Negative infinity to negative 1. And then this is where there's the debate. Do you include negative 1 or don't include? So honestly, whenever you're in doubt, always use an open bracket, because technically at that point at negative 1, the slope is 0. It's not positive or negative, right? So it's not really decreasing on that. Is there another one? Yes, between, so union, 0 to 2. And increasing on negative 1 to 0 and 2 to infinity. Any questions there? Okay. Okay, this is actually kind of exciting to do example 5. It is, because we're going to sketch, and they give you this information, and you have to kind of just sketch what's going on there. Okay, so what should we do here? I'm going to make a coordinate plane. x and y, or f of x, I guess. And it's like everything that we were so critical on in grade 12 about the, how this is all rough sketches essentially, except you have to have those critical values in there, but they don't really care if it's, arrows and stuff. So 0, 1, yeah, 0, 1 is a point, so I would probably label it 0, 1. And 2, 3 is a point. If you want, you could put ticks, but it's up to you. It doesn't have to be fancy. 2, 3, and 5, 0. So 2, 3, 4, 5, 0 is a point. So it's saying the slope is positive between 0 and 2 and 5 and infinity. So positive means it's increasing. So from 0 to 2, increasing. From 5 to infinity, increasing. Yes? Okay. Then what's happening here, from infinity to 0, it's negative, and from 2 to 5, it's negative. So it's decreasing. So now I made this look like lines here, but what's actually happening between this? It's a max and a min. It's not necessarily at a corner, right? Because it's saying it's a differentiable function, so I can't make it as a corner. Does that make sense? So maybe I'll just delete that. I just wanted to. Okay, so if it's decreasing, so it'd be going like this, 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 this. Yes? Is that what yours look like? He wasn't here.